Hello mathematicians, this is the second video on permutations and combinations, and today we are going to talk about how to find the number of possibilities for a combination and a permutation without using a tree diagram. So what is a smart cut that you can take? The first thing we're going to talk about is the basic or fundamental counting principle. Okay, this first thing I'm going to show you has to do with combinations. So if you're dealing with something that is a combination or something where order does not matter, we're going to use the basic or fundamental counting principle. Okay? So let's work through a first example. It says event X can occur in 3 ways and event Y can occur in 4 ways. So let's think of an example we might have. Let's say, for example, we're making a pizza and we say that event X, or the size of the pizza, happens in 4 different ways. And event Y, in 3 different ways, the size, and then event Y happens in 4 different ways, and let's say that that is the toppings. So what I'm saying is we're ordering a pizza. Let's say the pizza can be small, medium, and large. And we have 4 different toppings to choose from. We can have pepperoni, sausage, green peppers, or mushrooms. So knowing that we have 3 different sizes and 4 different toppings, we're choosing 1 topping, 1 size pizza. How many different combinations of pizzas can you have? The first thing we want to do is we want to say, okay, well, what are our categories? Well, we have size, and we have toppings, right? Then we want to say, okay, substitute the number of possibilities into each slot. So how many different sizes of pizzas do we have? We have 3 different sizes. How many different toppings do we have to choose from? We have 4 different toppings. And then we just multiply those numbers. That's a smart cut. So 3 times 4, that means that there are 12 possibilities, 12 possible combinations of pizzas. Now, that is a combination. It doesn't matter if we get a small pizza with mushroom or a mushroom pizza that's a small. That's one choice. This is the strategy that we're going to use to solve problems that are combinations, or problems in which order does not matter. So let's do it. So go ahead, take a minute. I want you to read number 1 on your own and use cups. So it says, for Friday's pizza party, there's an option of thin or thick crust. There are 3 different topping choices. There are also 3 different pop options. Use a tree diagram and the smart cut to determine the number of possible pizza combinations. I'm going to do the tree diagram first because I want you to see how the smart cut works and why it's more efficient. The tree diagram takes us a long time, so this is a little bit more efficient, right? So we have 3 different things happening. We have crust. I'm first going to list out my categories. We have crust. We have toppings, and I'm just going to put toppings, and we have soda or pop to choose from. So we have 2 different types of crust, thin or thick. So thin, and I'm just going to use a T for thick. We have 3 different pizza choices. So we could have, our topping choices, we can have pepperoni, sausage, or cheese. We can have pepperoni, sausage, or cheese. And then there's also 3 different pop options. So we're going to have to kind of fit this, right? But we have Coke, Sprite, or orange. And then if we have a thin pizza with sausage, we're going to have, and I'm going to do this one over here, Coke, Sprite, or orange. Thin pizza with Coke we have, or with a thin pizza with cheese, we have Coke, Sprite, or orange. Now we did the thin crust, now we're going to do the same with the thick. We have Coke, Sprite, or orange. We're going to have, again, Coke, Sprite, or orange. And then again, last, and I'm going to do this one over down here. Coke, Sprite, or orange. Now, this tree diagram, like it's taking up a lot of space because you're having to do a lot of things. But if I asked you, well, what are the total different number of possible combinations of pizza, toppings, and soda? Well, you could count up this last branch, and we'd have 1, 2, 3, and show you where I'm counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I got that there were 18 possible combinations using a tree diagram. Now let's see what would happen if we used our smartcut. Okay, so say, okay, well, how many different crusts are there? How many different toppings are there? And how many different pops are there? Well, there are 2 different crusts, there are 3 different toppings, and there are 3 different types of pop. So 2 times 3 times 3 gives us 18. Whether we use the tree diagram or we use the smartcut, we got 18 possible combinations. The smartcut is an easier way, a faster way, for us to figure out the number of possibilities. Let's look at practice number 2. It says draw a tree diagram that represents the number of outcomes of tossing a coin 5 times. Alright, so let's say, what is the thing that can happen when you toss a coin? You have, and actually to make this a little easier, let's make this the times we flip the coin, let's make it 3. Okay, I'm going to draw a tree diagram first. I'm going to say, okay, well, if I flip a coin, I'm going to have flip 1, flip 2, and flip 3, right? Well, what can happen when you flip a coin? Well, you can either get heads or tails. So on the first flip, I can either get heads or tails. Then I'm going to flip my coin again. What's the possibility that you get heads or tails again? Well, you're going to get heads or tails either way. So the second time you flip, you could get tails or heads again, right? If you got heads the first time, you could still get either one the second time. If you got tails the first time, you could still get either one the second time. And then the third time I go, I'm going to do it again. Well, I can get heads or tails again, heads or tails again, tails or heads again. This last one's going to be a little hard to draw because I'm running out of room. Heads or tails. So, how many different possible outcomes do I have? Well, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 possible outcomes. Now let's use the smartcut. Okay, well, I had flip 1, flip 2, and flip 3. I want to know what are the total possibilities on the first flip. I can get heads or tails, so that's 2 different outcomes. On the second flip, I can get heads or tails, so that's 2 different outcomes. And on the third flip, I can get heads or tails, so that's 2 different outcomes. So I'm going to do 2 times 2 times 2, which is 8 possibilities. So either way, I get 8 possibilities. Now, I'm going to do one more for you. Right, this time I'm not going to draw a tree diagram. I'm going to just write down, use a smartcut, and then I'm going to have you try 2 practice problems. So it says Raymond has 7 baseball caps, 2 jackets, 10 pairs of jeans, and 2 pairs of sneakers. How many combinations of the 4 items can he make? So the first thing we want to do is list out our different categories, or what we're choosing, what's happening. We're choosing from a baseball cap. We're going to choose a jacket. We're going to choose jeans, and we're going to choose sneakers. Now, what are all the different, how many does he have? Well, he said he had 7 baseball caps, he had 2 jackets, 10 pairs of jeans, and 2 pairs of sneakers. So how many total possible outcomes are there? Well, 7 times 2 times 10 times 2. That gives us 280 possibilities. So there's 280 combinations of cap, jacket, jeans, and sneakers that he can make. All right, I want you to go ahead and try to do example 4 and 5 on your own. Go ahead and pause the video and then press play when you're ready, and I will go over the answers. All right, here are your answers. You should have gotten 48 outcomes for practice 4 and 60 outcomes for practice 5. Notice on both of these, I'm writing out the categories. I'm showing how many are in each, and I'm showing that I'm multiplying. Part of showing your work on this objective is showing the categories. You cannot write 4 times 6 times 2. We don't know where those numbers came from, so your work needs to show that you know that you're doing shorts times shirts times shoes. So if you didn't make your work look like that, you should go back right now and make it look like that, and know that moving forward on this video, we need to see the categories in your work. All right, we're now going to talk about permutations, which is the other sort of counting principle that we can have. Combinations, remember, is where order does not matter. Permutations is where they do matter. So we are talking right now about permutations and the smartcut you can use for permutations. Now, to use permutations, we're going to use something called factorials. You see this exclamation point right here. Now, you've used that in your English classes as an exclamation point, but it also, in math, means a factorial. We would say, for right here, this means 5 factorial. And what that means is it's saying you take 5 and you multiply 5 by every number underneath it until you get to the number 1. So 5 factorial means 5 times 4 times 3 times 2 times 1. So 5 times 4 times 3 times 2 times 1, that's 120. 3 factorial, that means 3 times 2 times 1, or 6. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, which is 720. You also could do actually 6 times 5 factorial, because remember, the commutative property says that if we're multiplying things, it doesn't matter what order we multiply them in. So we could also just say that if you're doing 6 times 5 times 4 times 3 times 2 times 1, which is the same as 6 times 5 times 4 times 3 times 2 times 1. Okay, 6 times 5 factorial is still going to give you 720. Okay, in the same way, if we had 10 factorial, we know that 6 factorial is 720, so we could say 10 factorial is 10 times 9 times 8 times 7 times 6 factorial, because it's 6 factorial is just going to keep going down, 5, 4, 3, 2, 1, okay, and we get 3628800, or 3,628,800. Now, factorials are what we use when we're dealing with permutations. Remember, permutations happen when order matters. Okay, the order that something is happening in it matters. So as we go through these examples, I want you to think about, well, in what ways does the order matter? Why does the order matter in this question, and maybe it didn't matter in a different question? So let's look at example 1. It says a nurse has 3 patients to visit. How many different ways can she make her rounds if she checks each patient once? So first, let's think about what our categories are. What's happening, right? We have visits from a nurse. So we have visit 1, visit 2, and visit 3. Now, the first time the nurse makes a visit, she walks into the room and she has 3 patients to visit. The first time she makes a visit, she has 3 different patients to choose from because she hasn't seen any of them yet. So the first visit, she has 3 patients to choose from. The second visit, she's already seen one of her patients, so she only has 2 patients to choose from. The last visit, she's seen 2 of her patients already, so she only has 1 patient left to see. So the order that the nurse visits matters here because once she's seen 1 patient, she only now has 2 left to see. When she sees the second patient, she now only has 1 left to see. So this is an example where order matters. This is a permutation. We can still use the same principle as combinations where we multiply the different choices. So to find our answer here, we're just going to do 3 times 2 times 1, which gives us 6. There are 6 different ways she can visit her patients. Now, if we were to make a tree diagram for this, what that means is maybe she goes sees patient 1, then patient 2, then patient 3. Another possibility could be that she visits patients 3, then 2, then 1. She could go see patient 2, then 1, then 3. Or she could go see patient 1, then 3, then 2. Right? There's different orders that you can go see the patients in. That's what this means, that there's 6 different ways she can see the patients in 6 different orders. Let's do another example. High school teachers are to be issued a special code identification card that contains 4 letters of the alphabet. Okay? So let's think about what this is saying. This is saying we have some sort of code, right? There's 4 different letters. So our categories are going to be, we have letter 1, letter 2, letter 3, letter 4. Now, first of all, let's talk about why this is a permutation. If you have an ID code and your ID, right, that tells me that this is you and this ID tells me that that is someone else. If my ID code is ABCD, that means that my ID is ABCD. If I take that code and I rearrange it and I have my code be DCBA, that's a different code. So the order here matters. This is a permutation. You can't assume that all permutations are factorials that you just count down. You need to think about the context. So this says that there are 4 letters. It doesn't tell us anything about the letters repeating or not being able to repeat, so we have to assume that the letters can be repeated. So think about if you have to choose an ID code and you have, on the first one, how many different letters can you choose from? Well, there are 4 letters in the alphabet, so that means we can choose from 26 different letters. Now we're going to go to the second letter of our ID code. We are allowed to repeat. This question doesn't say anything about letters not being able to repeat, so I still have 26 letters to choose from. I go to my third letter in my ID. I can still pick from 26 different letters. My fourth, I can still pick from 26 different letters. Okay, think about it. We could have an ID that is A. We could have an ID that is AABB. We have all different options. So every single time we can choose 26 different letters. It doesn't matter if the letters repeat or not. Once we have our categories and then how many options we have within each category, we can go ahead and multiply. So I'm going to do 26 times 26 times 26, which gives me 9, 7, 6, or we have 976,000 outcomes or possible ID codes. Now let's look at 2B. It says, suppose now that the letters in the high school identification codes cannot be repeated. How many different identifications can be created? Okay, let's make our categories again. We're going to have letter 1, letter 2, letter 3, and letter 4. Now our letters cannot be repeated. The first time that I pick a letter, I have all 26 letters to choose from, so I have 26 options. Now let's say for that first letter I picked A. That means, since letters cannot be repeated, that I can no longer pick A again. How many letters would I have left to choose from if I've already used A and I can't use it again? You should have thought, oh, well, I only have 25 letters left. Now I've chosen A, I've chosen B, I can't use those 2 letters again, so how many letters do I have left to choose from? 24. I've chosen A, I've chosen B, I've chosen C, I've already used those 3 letters, so how many letters do I have left to choose from? 23. Now that we have our categories and our outcomes set up, we can go ahead and multiply. 26 times 25 times 24 times 23. So the total number of outcomes we have is 358,800, or 358,800 outcomes. All right, we have 2 more examples that I want to go through, and then I'm going to have you do a little bit of practice. So example 3. The digits 0, 1, 2, 3, and 4 are to be used on a 4-digit zip ID card. How many different cards are possible if repetitions are permitted? I want you right now on your own, try to write out the categories. What would the categories be for this card? So you should have had digit 1, digit 2, digit 3, and digit 4. Now, let's talk about the first digit. How many options do we have to choose from? Well, we have 1, 2, 3, and 4, so that's 5 numbers. So the first digit we can choose from 5 numbers. Now, repetitions are permitted, so that means that the next digit I still have 5 to choose from. Digit 3, I still have 5 to choose from. Digit 4, I still have 5 to choose from. So 5 times 5 times 5 is going to give us 625 outcomes. All right, one more example. Go ahead, example 3, or example 4. Go ahead and right now pause the video. I want you to try example 4 on your own. All right. Example 4. Again, if you did not pause the video and stop to do the example, you should pause the video now before I show you the answer to make sure that you're starting to comprehend how permutations work. Your categories for this one, you had 1, 2, 3. You're looking for a 4-digit ID card, and repetitions are not permitted, so your categories could be digit 1, digit 2, digit 3, and digit 4. There are 1, 2, 3, 4, 5 different choices for digit 1. Since repetitions are not permitted, that means after you use one digit, you can't use it again. So digit 2 only has 4 options, digit 3 only has 3, and digit 4 only has 2. So 5 times 4 times 3 times 2 gives us 120 outcomes. Alright, that is the instruction for today. What I would like you to do right now is I want you to try to do a couple of practices. So try to do right now practice 1, 2, and 3. Let's do these first 4 practices. I know it says the number 3 twice, but let's try to do these 4 practices right here. Go ahead, pause the video, and then press play when you're ready, and you can see the answers. Alright, here are the answers. Let's quickly just run through each of them so that we make sure that you feel good about why they're organized this way. Number 1, if she's choosing from 8 different contestants, that means that once a contestant is chosen, they're not going to perform again. So you have 8 different contestants. Contestant 1, 2, 3, 4, 5, 6, 7, 8. The first contestant, you have 8 to choose from. After that, everyone has 1 left. So it's 8, 7, 6, 5, 4, 3, 2, 1. 2, you have 3 different things you're choosing from: lots, styles, and floor plans. So you have 4 lots to choose from, 3 houses, and 5 floors. which gives you 60 possibilities total. For this one, you have 18 members on its roster, and the coach is picking 3 players out of those 18. So we have a first batter, a second batter, and a third batter. The first batter, you have 18 people to choose from. The second batter, someone's already batted, so you only have 17. The third batter, 2 people have already batted, so you only have 16. And then the last one, you're visiting 4 different parks this summer. You have Park 1, 2, 3, and 4. You have 10 to choose from, so it'll be 10, 9, 8, 7. Now, before we go today, I want you to look at each of these, and I want you to write down, what do you think each of these are? Are they a permutation or a combination? Remember, a combination is when order does not matter, so it doesn't matter the order you do things in or the order you list things in. The second is permutation. That is when the order does matter. It does matter the order that you write or that you list things in. So go ahead. Take a minute, pause the video, and I want you to just write a quick P or a C next to each of these questions. Alright, you should have said that the first one was a permutation, right? The order matters because if Molly performs first and Ann performs second, the order they're performing in matters. 2, this is a combination. The order that you choose, a lot, a house, and a floor plan, that doesn't matter, right? If you have a big lot, a small house, and type A floor plan, it doesn't matter what order you list those out. You could have a small house, a big lot, type A floor plan. It's the same thing. Number 3, the order does matter. It's a permutation. Batting order matters because if John is supposed to bat first and Mike is supposed to bat second, then it's John and then Mike, not Mike and then John. The order matters. And then the last one would also be a permutation because if you're visiting ballparks and you're going to go to Chicago, then New York, then Los Angeles, and then Detroit, that order matters. We're going Chicago, Los Angeles, New York, Detroit. We could not say that in a different order. If we said Detroit, New York, Los Angeles, Chicago, that's a different order. So order matters. All right, that's the end of this video. Write down any questions that you might have and come to class ready to practice.